All right, and we're all set. We're recording. So good morning, everyone. My apologies for getting the last video posted so late. I was in meetings all day on Wednesday following class. And so I decided I could get it done on the Thursday morning before my next meeting started. But then my power was out all day yesterday. So I got it as quickly as I could, which was late last night. So that's all of section 14.1. The video is now posted. We're into section 14.2, and this is limits and continuity of functions of multiple variables. So multivariable functions. And I'm just going to start off with a problem. We've got two functions here. F of xy is equal to x squared over x plus y. And another function g of x is equal to x over x plus y. Now, what I want to get out of this problem is that limits are a little bit more subtle in higher dimensions than they were in Calculus 1. And so that's going to be sort of our running theme of today, is that there's a little bit more subtlety. And the reason is because, well, a limit is all about as you approach a particular point in the domain of the function, what are the function values doing as you get closer and closer and closer to a point? In Calculus 1, there's only really two directions you can approach an input from. You either approach it from the left or the right. And then you can sort of correspondingly work out the left-hand limit, the right-hand limit, see if those values are equal. If they are, then that's the value of the limit of the function. But in multivariable functions, you can approach from many different directions. In fact, infinitely many different directions you can approach a point in the domain xy, because you can come at it from any direction in the xy plane. That's where the subtlety lies, is when we want to talk about the limit of a function, it has to be regardless of which direction you're approaching it, regardless of the infinitely many. So we've gone from two directions in Calculus 1 to infinitely many directions to approach a point in Calculus 2. And that's where the subtlety lies. And that's what today's session is really about, is trying to wrap our head around this subtlety. So we're going to get into that with this following problem. We've got this function f, and we're going to fill out the table. So let's work out what is the limit as x goes to 0 of f of x comma mx. Now that's just a function of one variable now, because you'll notice that we've replaced the y variable with mx. So ultimately, this is a function of one variable, and it's something we know how to work out. So let's actually just go ahead and work that out. So I'll write down what f x mx is. M is just some arbitrary constant. We haven't specified what it is, so it's just some constant. It could be the value 2, it could be the value pi, it could be the value 1032. It doesn't matter, it's just some constant, it's not changing. The limit is with respect to x. X is the thing we're imagining changing. So this is x squared over x plus mx. We can do a little bit of simplification with this expression. There's a common factor of x in both of the bottom terms, so we can factor that out and get a 1 plus mx. Sorry, 1 plus m. The x is gone now because it's canceled. So there's our function. And now we want to evaluate the limit. So the limit as x goes to 0 of fx mx is just the limit as x goes to 0 of x over 1 plus m. And what is the value of this limit? Again, just keep in mind that m is some fixed constant, it's some number. Whatever it is, it's not changing. What's the limit of this expression as x goes to 0? Yeah, it's 0. The top's going to 0. The bottom is a constant. And so the ratio is going to 0. Okay, so we've done a calculation. What does this calculation even mean? Well, what it's saying is the following. I'll draw one picture, and this is going to apply for both of these. So we've got our domain xy, and we are imagining now that in this domain, the set of all points in the plane xy that we're plugging into either f or g. Sorry, g, I just noticed now g is supposed to have a comma y in there because it's a 2-variable function as well. There's supposed to be a comma y in there. So both of these functions, f and g, are functions of 2 variables. And what we're doing in the table, the first thing we do is set y equals to mx. What that means is we are only restricting our points to live on the line y equals mx. And so that's what we're thinking about as the points we're plugging in the function. Only the points that live on this green line. We're now restricting the set of points we're plugging into our function to live on the green line. And in the limit, we're then saying what happens as these points move towards the origin, move towards 0, 0. What is our function value doing at points that live on these lines that get closer and closer to 0? And this first calculation we did says that, oh, the function f, the output, is going to get closer and closer to 0 as our inputs move along this line, getting close to the origin. The second function, we can do the same thing. G of x, comma, mx. That is x over x plus mx. And again, we can simplify. That's 1 over 1 plus x. Sorry, 1 over 1 plus m. I keep wanting to write the x there. 1 over 1 plus m. So that's just simplifying by canceling out the x. And now we want to calculate the limit as x goes to 0 of this function. And what is that? Well, that's the limit as x goes to 0 of 1 over 1 plus m. And again, m is just a constant, so 1 over 1 plus m is just a constant. In particular, our table wants us to consider 3 different values for m equals 1, m equals 2, m equals 3. But at this point, we can say, well, that's just a constant. So the limit of a constant function is just the constant. And so this is for any m. So maybe I'll write that in here. This was for any m. In particular, I have to worry about m being -1 because then there's division by 0. So this is really happening for any m not equal to -1. So in particular, it works for our m values 1, 2, and 3 in the table above. And so now we can fill out that table. We have 0, 0, and 0. So in terms of our picture above, we have, and I'll modify this a little bit. I'll get rid of that m. That looks like a y equals x line. We also have a y equals 2x line. Maybe I'll draw up here a little bit more so I can label it. And then we have a y equals 3x line, something like that. And this is saying that no matter which line I'm considering in my domain, if I let the points live on that line and approach the origin, then my function value f at those values on that line are going to 0. No matter which line I'm on, my function value is going to 0. That's what that first line of the table says in our calculation in orange. What does the next calculation say? The next calculation says that, well, now for g, it really depends on which line we are taking our points on. If we're on the line y equals x, so m is 1, then as we let our points travel along this y equals x line, then our function value goes to 1 over 1 plus m, or 1 over 1 plus 1, or in other words, a half. So our function values approach a half. But if I move along a different line towards the origin, y equals 2x, if I go along that line towards the origin, I get a limiting value of 1 over 1 plus m, in this case, 1 over 1 plus 2. So I get a third. So this is where we're starting to see a subtle difference in that now I've got a direction. If I go along y equals x, my function values g approach 1 value, they approach a half. But if I slightly change the direction I'm approaching the origin from, my function values are now going to a third. And if I slightly change it even again, my function values are going to a quarter. If I go along the line y equals 3x. And now we can see that there's infinitely many different directions. I can really take m to be anything I want. If I'm coming along y equals 10x, then my function value is going to approach 1/11. And so there seems to be some suggestion here that these functions are very susceptible to which direction you're approaching a particular value from as to what their limits are, what their limiting values are. In the first case, we would say that the limit exists and it's 0 because it didn't matter which direction we were approaching from. Well, there's even a slight subtlety with that. I've only checked going along lines. Maybe there's some funny way to approach the origin, sort of curving around. I'll draw this in, but then I'll erase it quickly. Maybe there's a way to approach the origin so that if I let my points run along this curve, my function f approaches a different value entirely from 0. It may approach some other value. And this is meaning that limits are a tough cookie to crack when we're in multiple dimensions. So that we're going to have to define what we mean by a limit and then look at some examples of these subtle points. So what this example illustrates is that as we move towards a particular point, in this case the origin in our domain, our function values can behave differently depending on the direction that you approach the point. That's what that function g was telling us. If we go along different lines, we can get different values. You know, it might be worth just plotting this. Let's bring up our plotting utility. So this is going to be x over x plus y, x over x plus y. There it is. And you can see it's having some real issues along. What is that? Where is it having issues? What parts of the domain is it having these strange, quite intense vertical bars happening there? Anyone in the chat want to tell us? Yeah, the line y equals negative x, because that's where the denominator is 0. And then we see that it's sort of, as we get close to that line y equals negative x, it's either blowing up or it's blowing down. It's going off to negative infinity. But these lines that we looked at, y equals mx, they are just different ways we can come to the origin. And the different ways we come to the origin are really about sitting on part of this up, this part that went up. Maybe we can travel along it, along the same level. And that's exactly what we found, is that if we move along, say y equals x, these points are all at the same height, 1/2 or 1/2. So the limiting value as I move along this is going to go to a half. But if I change my angle of my line a little bit, then I'm on another portion at a different height. And so that's what we've detected with our calculation, that if we approach the origin along different lines, we are at different constant heights of the curve. And so our limiting value is that 1/1 plus m. But in general, there's some funny stuff that's going on here. And so we wouldn't want to say the limit exists at 0, because it depends on how you approach it as to where you end up. All right. I'll just cancel that and drag this out of the way. So let's get to a definition of what a limit is, and then we'll figure out ways to calculate it. So here's our formal definition of what a limit is. Let f be a function of 2 variables, and d is its domain. And let's consider points that are arbitrarily close to AB. We say that the limit of f of x as xy approaches AB is some value L, provided that, and here's where things get a little bit more formal, a little bit more complicated in terms of what this means, but we'll draw a picture and get an idea for it. So if for every epsilon greater than 0, so for every small positive number, we're thinking, there is another small positive number, delta, greater than 0, with the following property. The first line says that if the point is that whole square root business, that's just a distance. If our point xy is within delta from AB, so that's what that is. This is just a distance between x, y, and AB. So if the distance between our point that we're looking at in the input and AB is less than delta, then our function value that comes out is within epsilon from what we're calling the limiting value L. Okay, so this picture that corresponds to this definition really comes along with a picture, and here's what the picture looks like. So I've got my coordinate axes. I've got my my surface sort of sitting here. I'll try to draw it with a little bit of perspective. There's our surface sitting up there. And we've got a point in our domain. We're going to call that point AB. And I want to show that, or I want to argue what the limiting value of this is. So I'm going to go up here and say, this point L, or this value L on the z-axis, that's the limiting value of the function as we approach AB, provided something happens. What do I want? I want to capture the idea of what it means to be a limit. So I'm going to go ahead and draw that point on here. And what I'm going to say is, that's the limiting value if I can get my function values as close as I want to it by taking my inputs as close to AB as I want. So again, the subtlety here with limits is you never want to actually evaluate the function at the point AB, because that makes no difference in terms of the limit. The function doesn't even have to be defined at a point in order to talk about its limits there. And you think back to calculus 1, we wanted to find the limiting value of a function at a point, and maybe there's a hole there or a vertical asymptote there. We wanted to look at how the function behaves at that point, or near that point, I should say, not actually at it. So the idea is, if I can, for any epsilon, make this little, epsilon neighborhood sort of sandwich around this point L, and I can find some circle. This is my delta circle, radius delta. So I can find some small delta such that when I take that radius delta circle about my point AB, whenever I have a point XY in that radius delta circle, that's this first line. That's what that's saying. XY is in that radius delta circle about AB. Then when I evaluate the function at that point, I land inside the epsilon sandwich about L. And if I can do this for no matter how thin I make this sandwich I want, this epsilon sandwich, no matter how thin I want to make that, I can always find a circle around my AB value such that all other values map to within that epsilon sandwich. Then I say that L is the limiting value. It's the formal way of saying the limiting value is L if my function values can get close to L as I like by taking my inputs as close to AB as I like. This is the formalization of that. So it's tricky, it's a little bit challenging, it takes a lot to digest. I'm not going to be testing you on this formal definition, but I did want to introduce it because this is the kind of formal definition you would use when you go into other courses, maybe 322 complex analysis. You do spend a lot of time on epsilon delta definitions for limits and other things. And you may see it come up in some of your other courses as well. So I just wanted to introduce it to get sort of a feel for what kinds of ingredients you would need for formal definitions in order to prove things from them. But I'll do one proof using this just to get a flavor for it, but then we'll do a different way of showing the limit exists.
Sorry, can I ask you a quick question before we move on?
Sure, go for it.
So on the graph that you've drawn for point L, in the little cloud shape, there's two dotted lines above and below it too. What are those for?
Yeah, the blue lines. So
Mm-hmm.
I'm thinking of those as the upper and lower crusts, if you will, of my sandwich, or slices of bread of my sandwich. So those are above. So if I go epsilon above L and epsilon below L, then that gives me what we have is like an epsilon sandwich. So I've got L is like the main topping of my sandwich inside, and then my upper slice of bread is epsilon above the main topping. My lower slice of bread is epsilon below the main topping. And that's capturing this statement here, because I want my function value at an arbitrary point xy in this circle down below. When I take its function value, it's going to come up and be measured along the z-axis. I want it to live inside the sandwich. So I want it to be within epsilon of my main ingredient. That means it's in between the two slices of bread as well. Does that make sense?
So we're giving it like a kind of a domain, right, for the sandwich?
Yeah, we're essentially giving it a target. I'm saying I want this epsilon target. So you got to be able to pick things in the domain so that when you take their function value, you land inside the sandwich. And my target is, here's how wide my slices of bread are. You got to make sure you land inside them. If I squeeze my slices of bread closer together, you may have to squeeze your circle around AB to be even smaller. But if you can do it for some delta small enough so that that circle around AB, any point inside that when you map it up, lands inside your sandwich. And you can do that regardless of how thin your sandwich is. You can always find a circle that's small enough that everything lands inside the sandwich. Then we say the limiting value is L. I'll give you a one-dimensional contrast for this. So from Calculus 1. So I'll pose it as a question first. There's our function. Does the limit exist at A? So does our limit exist at A? So here's our function. I've sketched it in green. Does our limit exist? Yeah, the limit does not exist at A. You'd probably argue this if you were in Calculus 1. You'd say the limit doesn't exist because the left-hand limit is one value, namely the lower value, and the right-hand limit is that value of the whole, and they don't equal each other. Left hand doesn't equal right hand, therefore the limit doesn't exist. So let's apply the sandwich idea. Let's say I want to show that the limit does exist. I'm going to fall into a trap because the limit doesn't exist, as we've already sort of indicated. But let's say I'm thinking I'm going to show that the limiting value, I'm not going to write L in there. I'm just going to say maybe this was a height of 2 is that horizontal line. And then the other height of the horizontal line is 3, just to be a little bit more concrete. Let's say I want to show that the limiting value is 2. Well, to do that, I'd have to be able to, for any sandwich I make around 2, so I'll make a little sandwich around 2. There's my top slice of bread. There's my bottom slice of bread. Maybe the distance between the bread and the topping I'll take to be 1/4. Some really small value. I'm just being concrete here, but that's my epsilon. So I take a really small value. I made this sandwich, which between the topping and the bread is 1/4, so the full thickness of the sandwich is 1/2. In order for the limit to be 2, it means that I have to be able to find a circle around A, or in this case, since it's 1D, an interval around A, such that anything in that interval will land in the sandwich when I take the function value of it. But I think you can already see a problem here. If I take a value on the right-hand side of A, I'm going to zoom in a bit. If I take a value on the right-hand side of A, its value that it takes does not live inside the sandwich. And so that tells me that for this particular epsilon is 1/4, I cannot find a delta. I cannot find a small enough circle around A. I'm calling it a circle just to be the analogy with our functions in two variables, but in this case, it would be an interval. I can't find a small enough circle around A so that all the points within that circle about A, when I take their function values, lands in my sandwich. And this is telling me then that the limit can't exist because I can't get my function values close to 2 as possible by taking my inputs as close to A as possible. There are many values that are close to A, but their function values are going to be of height 3. So that's the idea of what we want to, I'm trying to capture the idea of what it means to not have a limit. There are values close to the point A, which the function values just aren't close to the value you're trying to argue is the limit. So this is, the limit won't be 2. And by a similar argument, the limit won't be 3 either, because there are values on the left-hand side of A that are value of 2, which are never getting close to 3. Does that help? That sort of analogy?
Yeah, it does. So the same thing exactly applies to that 3D vector, to the plane section, right?
Exactly, yeah. So in this particular case, it looks like my function's nice and smooth. There's none of this discontinuity happening. I'm using these smooth discontinuities, but these are all terms that sort of come up when you talk about limits. So I'm using them prematurely, but that's the kind of idea that we're trying to get a hold of. So what we're going to do in these next few examples, actually, we're just going to do a bunch of examples, is we're going to try to show either limits exist or they don't exist. So in this case, the first one, we're going to evaluate the limit or show it does not exist. So we're going from x, we're going to 0, 0. So I'm thinking of, I've got this function, what's happening as my inputs x, y get closer and closer to 0. Now, if you're thinking, let's just do what we did in Calculus 1, then that's perfectly reasonable to do. In Calculus 1, probably the very first thing you would do if you were asked to evaluate a limit is just try to plug in the value, right? See if it works. And in this case, when I plug 0, 0 into my function, what do I get out?
It's going to be not defined.
Yeah, exactly. 0 over 0 in indeterminate form. So our first gut reaction, evaluate the limit, plug the value in. That's a reasonable reaction, but then we run into a brick wall here. We're like 0 over 0, not defined. Okay, there must be something else I can do. So what am I going to do with this case? There's a couple of things we could do. We could get a feel for this, and maybe I'll just get a feel for it right now. Let's say we're approach 0, 0 along the line y equals 0. So to have our x, y values go to 0, 0 means that we want to get closer and closer to 0, 0 and see what happens to our function. So what we could do right off the bat is just maybe pick a direction, come along the line y equals 0, or in other words, the x-axis. So we're coming along the x-axis. And in that case, if I'm coming along the x-axis, then my function is going to be, I'm going to plug in x equals x and 0 for y. So I get x squared over root x squared, or x squared over the absolute value of x, because the square root of x squared is the absolute value of x. X squared divided by the absolute value of x is just the absolute value of x. And so when I come along the x-axis, my function values are just going to be absolute value of x. And if I get closer and closer to 0, the origin, 0, 0, then this is going to 0 as x, y goes to 0, 0. So this tells me that as I approach along the x-axis, my function value is going to 0. So if the limit of this function is to exist, I already know it's got to be 0. But this isn't enough to tell me that it is 0 for any direction. Just says that if I come along one particular direction, it goes to 0. So if the limit exists, that number is independent of the direction you approach from. So the number would have to be 0 that the limit is. But maybe it's not. Maybe there's a different direction that if I approached along another direction, it gives me a different value. So at this point, we know one of two things. Either the limiting value is 0, which we still have to show, or the limit doesn't exist, which we have to find another direction to approach the origin from, which we get a different value, much like we did in our motivating problem. For that function g, we took different lines to approach the origin from, and we got values of a half, a third, a quarter. So those were all different values, so the limit didn't exist. All right, so, what could we do here? Well, maybe I'm going to say, I'm going to try to show that the limit does exist. And this is the one and only time I'm going to use an epsilon delta argument, just so you get a feel for it. So we will show the limit is 0. Okay, the reason I did that first step was it gave me a candidate for what the limit should be. In order to do an epsilon delta argument, notice how it says in the statement itself, we have to know what the value L is that we're trying to prove is the limit in order to prove it's the limit. So we had to have a candidate for what we thought to be the limit in order to show that that is the limit in this epsilon delta argument. So that's why I did this first little step of let's approach along a line, convert it to a limit of a single variable. We get a candidate now. If the limit exists, it should be 0. Let's try to show it. And so we'll do an epsilon delta argument, just so you get a feel for what they are. They kind of look like magic when you first see an epsilon delta argument. The first one here you're going to see is going to be, you're going to say, well, it doesn't look like you did anything. And sometimes it doesn't look like you did anything. But I just want you to have exposure to one argument of this form. And then you'll get more practice in your future classes if you do some analysis classes. So here's what we're going to do. We're going to start it by saying we are given an epsilon bigger than 0. We are given a thickness of a sandwich we are trying to show our inputs are going to land in. So we're given an epsilon greater than 0. And then I need to choose that circle size down below. I need to choose its radius, the radius of that circle around the origin. So I'm going to choose delta to be, and I'll fill in the blank after. This is where it kind of looks like magic. So I'm going to choose delta, and I'll come back and fill that in because I don't know how to choose it just yet. Maybe I'll put it in a brighter color here. Got to come back and fill in that blank. Okay, so we choose our delta. And now we just write out what the statement says. Then for xy in the domain such that xy is within delta from the point we're approaching in our limit, which is 0, 0. So this line just says, so then for xy in the domain such that it's within that delta circle of the origin, I want to show that the function value of xy is within the epsilon sandwich of 0. So then I'm just reading the sentence again. Then for blah, 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 we have, and I want to show that the function value at xy is within epsilon of my value that I'm claiming to be the limit, which is 0. So I want to show that this quantity is less than epsilon. It lives in the epsilon sandwich. And so I'll write it out. This is x squared minus y squared over the square root of x squared plus y squared, absolute value. I can do a little bit of algebra here. I can make that thing on the bottom as an x squared plus y squared, and I'll multiply by a square root of x squared plus y squared on top. So what did I do? I just replaced the square root of x squared plus y squared on the bottom by a square root of x squared plus y squared over the square of it. So if you just look closely, what I did was I just used this to replace this. And that's fine because the bottom is the perfect square of it. So it's x squared plus y squared. You can write that as the square root times the square root. And so all I'm doing is just noticing that one of the square roots on top cancels with one on the bottom, and it would leave you with the square root on the bottom, which is the expression on the left. Why have I done this? The reason is because I know how big this is. x squared minus y squared is going to be a smaller number than x squared plus y squared. We got absolute value signs around here. So the magnitude of the difference of those two positive numbers must be smaller than the magnitude of their sum. So this has to be less than the absolute value of square root of x squared plus y squared. I can get rid of those absolute values because we're already looking at the positive square root. So in other words, this thing was less than 1. And so I just used that. What I'm trying to show is that this function value is within epsilon of 0. So I'm trying to show that this whole quantity is less than epsilon. Right now, I've got that this whole quantity is less than the square root of x squared plus y squared. And I know that the square root of x squared plus y squared is less than delta. So I know that this thing is less than delta. And I want to show that that's less than epsilon. So if I just choose the circle that I've used as my sort of collar around the origin, where I'm allowed to take points to take the function values up, I just take that to be the thickness or half the thickness of the sandwich, which was epsilon. So I just choose delta to be epsilon. Then I get my result. This is actually less than or equal to. They're equal to, so maybe I should have just written equal to here. And there we get our result, that my function value is strictly less than epsilon. And so if I choose points that are within my delta circle of the origin, then my function values are within epsilon of 0, and that proves it. So therefore, the limit is 0. And again, I said it kind of might look like a little bit of magic. And it does take a lot to digest this. So I don't expect you to get this all in one go, but I did want you to expose you to it. Now I want to do some proofs where we actually don't use the epsilon delta argument and do things that are a little bit more familiar to you. And I'll give you a hint. In fact, what we're going to be using a lot of is the squeeze theorem. We're going to use the squeeze theorem a lot to show that limits exist. So let's get to some more examples. So we've just proved that the limit of that was 0 using an epsilon delta argument. Let's see some more examples where we show limits exist and some that don't exist. So for this one, I want you to just take 30 seconds or so, do that gut reaction that you would do. What's your very first reaction? What's the value of this limit? What's your very first reaction you should do? Yeah, just see what happens when you plug the value in. Yeah, we get a top goes to 8. The bottom is going to 0. So what's the ratio doing? So what's the ratio doing? You got a top that's going to 8, and the bottom's getting really, really, really small.
It's an infinite ratio.
Yeah, it's going to be infinite. So you don't know if it's going to positive infinity or negative infinity, because it really depends on whether the denominator is going to 0 from the right or 0 from the left. So 0 through positive values or negative values. But from this alone, we see that the top's going to a constant, non-zero. The bottom's getting really small. So the ratio is blowing up. It's getting big. And so from this alone, we see that the ratio gets bigger and bigger. Therefore, limit does not exist. Okay, so we can still use our results from Calculus 1, our familiarity with limits from Calculus 1. We can still use those ideas. We got here a ratio. The bottom was getting small, going to 0. The top was going to 8. So the ratio is getting bigger and bigger. So it won't settle down to a particular number. So how about the limit laws? These are going to be things that are going to be useful for helping us compute limits. We get all the same limit laws we had before. If the limit of the function f is L, the limit of the function g is m, then The limit of their sum is the sum of their limits. The limit of their product is the product of their limits. The limit of the ratio is the ratio of their limits, provided the denominator isn't 0. And the squeeze theorem also holds for multivariable functions. These would be formally proved using the epsilon delta definition of the limit. Once we get these, we are now able to use them. And so that's the idea, is I'm not going to prove these with the epsilon delta definition. I've already given you the one proof I'm ever going to show you with an epsilon delta definition. But we can accept these now as facts that we're allowed to use about limits. Let's go ahead and see how we can use these ideas. So we want to find this limit if it exists. Again, our very first reaction, plug the value in, we get a 0 over 0. This is an indeterminate form. If it was a single variable case, you probably would use something like L'Hopital. I'm thinking that's what the reference to Laplace was in the chat. Is actually meant to be L'Hopital. But yeah, there's, you know, in the one variable case, you would have L'Hopital. Here we don't. We don't have L'Hopital's rule. But you could do things like, let's find different directions. See if I go along a line y equals mx, what's happening. Maybe it behaves the same along every line, in which case that's still not enough, because I need to show that if I approach along any direction, no matter if it's a line or not, as long as I approach along any direction, it goes to the same value. So let's see how we can prove this. So what I'm going to do is I'm going to just maybe I'll write it like this. So we'll let this be f of x, y. And I'm going to look at what f of x, y is. I'm going to see how big is this thing. Now let's just look at its magnitude. So that's 2xy squared over x squared plus y squared. And I'm going to try to pick it apart, much like we sort of had in our epsilon delta definition. I can kind of use some of the tools we used inside there. I'm going to pick it apart and look at this ratio. Can anyone tell me what the biggest this ratio could be? What's an upper bound on this? Maybe you want to think in terms of relative size. Yeah, it's 1. So y squared is less than or equal to the denominator, x squared plus y squared. So this ratio is at most 1. And that means that this is at most this. So the magnitude of the function is at most 2x. And as xy goes to 0, 0, what does this 2x go to? As xy goes to 0, 0, it goes to 0. So what we have is the following. Just wanted to make sure I wasn't giving something away of the next line. So what we have is the following, is that this function, so we've got the limit as, maybe I'll write it this way, xy of going to 0, 0 of f of xy. So I'll put a little bigger than or equal to 0 because I've taken absolute values. That's why I've taken the absolute values there. So when I take the limit of the sides of the inequality, then because our absolute value of our function is bigger than or equal to 0, the limit has to be bigger than or equal to 0. But because of our absolute of f of xy is smaller than or equal to 2, absolute value of 2x, then it means that the limit has to be smaller than the limit of 2x. So I basically just took that inequality I had above and took limits of all sides. And this just says that if an inequality is satisfied, then taking the limits of both quantities in the inequality, it still remains satisfied. And this is equal to 0. Because as x gets close to 0, 2x gets close to 0. And so we've got that the limit of our expression is trapped between 0 and 0. We've just squeezed it between 0 and 0, so it must be 0. So by the squeeze theorem, the limit is 0. So this is the most typical way of how we're going to evaluate the limit. We'll just try to analyze the expression, see if we can convert it to an upper bound that involves just a single variable. And we use the squeeze theorem because we can evaluate the limit of that single variable function. All right, so we get the same kind of ideas that we had in calculus 1. We say that a function is continuous at a point if the limiting value of the function is equal to the value of the function at that point. So the limit as xy goes to ab of the function is equal to f of ab. That's what it means to be continuous. The limit is equal to the value of the function. The function is said to be continuous on a set if it's continuous at each point on the domain. So let's go ahead and look at this next example. Let's find the value of k so that this function is continuous. So it looks like for xy values not equal to 0, so for any other xy value, 1, 2, pi, and e, whatever the x and y values are, as long as they're both not 0, we have no issues evaluating the exponential. So the exp, if you didn't catch what this really means, it's just the full name of e to the negative 1 over x squared plus y squared. That's how we would write it in a computer, for example. We would write exp and then in parentheses the input, and that's just short, or I shouldn't say shorthand, that's longhand. That's longhand for e to the power of. This function has no problems at values where x and y are not both 0, because we can divide by them. It's a positive or non-zero number. It's in fact positive, and there's no problem taking e to the negative of that exponent. So all of those things are fine. So everything behaves nicely except at the origin. At the origin, this expression doesn't make sense. So we've defined its value to be k there. And the question is, what should we make the value of k so that this function is continuous at 0, 0? Well, to be continuous at 0, 0, we want the limit as xy goes to 0, 0 of our function f of xy to be equal to the function value at 0, 0. That's what we want to be satisfied. And let's use the given information. So what is f of xy? Well, the limit as xy goes to 0, 0. Again, we only worry about points xy that are close to 0, 0, never actually at 0, 0. So for our function, I can use the first piece of the expression. That's that. And I want that to be equal to f of 0, 0, which is k. And what is the value of the limit? Again, use your gut. Use your gut here. What's the value of this limit? What do you think it is?
Just 1.
So let's have a look. The denominator is going to go to what in this case? 0 squared plus 0 squared. So that's going to 0. The top is going to negative 1. So what's the ratio going to? We got negative 1 over a number that's going to 0. It's actually always a positive number, so it's, I'll maybe write a 0 plus. So I got negative 1 over a really small positive. What's that quantity doing? Yeah, that's becoming a really big negative. So this is going to negative infinity. And then we're taking e of that number that's going to negative infinity. Exactly, so that's going to 0. So this whole thing is going to e to the negative infinity. That's sort of an abuse of notation. I don't really like to write negative infinity as if I'm plugging it in, but this, I'll put quotations around it, as in, this is what we're thinking. It's going to e to a really big negative, and that's 0. So k equals 0 to be continuous. To be continuous. So the point with some of these examples is to show you can still use your gut. You don't have to go through some formal calculation. You can still use your gut to tell you if the input's doing this, the output's doing this. I'm going to do one more example just as a contrast, and it's going to be this one here. First one. Let's test for continuity at the origin. I'm going to give you some hints here. Let's go along the line first, y equals 0. And then second, go along the line y equals x. So I want you to tell me, if you go along the line y equals 0 and approach the origin, what is your function doing? So that is, we are looking at f of x 0. And this one is we are going along the line y equals x. So we are looking at the values f of x, x. So if I go along the line y equals 0 on the first one, what is f of x 0 equal to? F of x 0. Yeah, that's 0. So this says f of x y goes to 0 along the line y equals 0. And what about this next one? F of x, x. Well, we plug that in, we get an x squared, we get an x squared plus an x squared, or in other words, an x squared over 2x squared. What does that simplify down to? Yeah, half. And we still haven't even let our x values go to 0. So this f of xx is just constant. It's always a half when you're on the line y equals x. So this says that f of x y goes to a half along the line y equals x. And what can we conclude from this? Does it matter how we approach the origin? Does it matter if we go along one line versus another line in terms of where our function values are heading? And this tells me it does. If I go along one line, my function values go to 0, but if I go along a different line, my function values go to a half, and so therefore the limit does not exist. So therefore, limit does not exist, because if it were to exist, my function values would have to approach that value regardless of direction. But this is already showing me that if I approach along different directions, I get different values. I'll give you a visual for this, and then we'll call it for today. So here's our visual. I'll shrink it down so you can still see behind. So this is the graph of that function. Make sure we can see it here. Where are you? X, Y. Oh, it was there. There it is. Xy over x squared plus y squared. So you see there's sort of a kink in it. And what we've just done is we've said if we took our slope to be 0, so m to be 0. So if I go along this line, my points, as I move along that line, my points are just going towards 0. They're always at a height of 0. Whereas if I take a different line, the one with slope of 1, and move along that one, my function values go to a half. Notice that as soon as I drop it right on 0, the point disappears. Can you see that very closely, that the yellow point is disappearing? That's because this expression is not defined right at the origin, because that's what we're trying to figure out what's happening there. It's actually not defined there. But this says that if I move closer and closer to the origin along those inputs, the inputs are in the gray down below, and our output's the yellow point, then my function value is getting closer and closer. In fact, it's always a half. It's going towards a half. So depending on direction, my function values are going to different values. So this would not have a limit there. And you can kind of see it's very weirdly behaved. It looks like it's got a kink in it, or it's crumpled. And this is an indicator of not having a limit exist. All right, so that's it for this section. There's a few more examples. I will fill in the examples by hand, but they're just exactly this one, just done a couple more times. So I'll give you a couple more done that'll be done by hand. I'll maybe even put them in a video as well. But that'll be it for this section. So let me just stop the recording.